This section is very mathematical, but also very, very necessary for success in this course. It talks about how are we going to treat a concentration of a solution. We could treat it in a qualitative manner and say concentrated versus dilute. I think of orange juice, frozen, it is concentrated, dilute in the refrigerator case. But let's say we want to make a quantitative measurement. We're going to have to actually measure a value. We're going to use the concept of molarity. No one has trouble with moles of solute. What people have trouble with is the manipulation, especially when you come to the liters of solution. So let's begin with the most basic problem. We want to know the molar concentration, could also be called molarity, could also be called moles per liter. If a solution has 2.8 grams of a solute in 250 mils of solution. So I've already set a lot of these up so I can take time to talk about what I'm doing. There's my 2.8 grams of KOH, there's my given amount of solution. What I'm going to do then is use the molecular weight of potassium hydroxide. So if I take a look at my notes, I see that it is 56.1 grams for every mole, and again, that is the molecular weight. And since I want to know the molar concentration, I need to turn those milliliters into liters, and I will come up with 0.1996 moles per liter, or, being correct, 2.0 times 10 to the minus 1 molar. You may see a problem like that. You may see a problem like this, where you have to do an interconversion. So why do we use molarity? Because it's really easy to find a volume using a burette if we have a stock solution. So this one says, what volume of the, and I changed it to an actual amount of NaCl. What I did is I made it into a 5.43 molar. That makes the problem a little bit easier to discuss. If I want 10 grams of sodium chloride from that stock solution, what will I do? Well, it says that I want 10 grams of sodium chloride, and I know 1 mole of NaCl is 58.44 grams. I'm using the molecular weight, and now what I'm going to use is the concentration of the stock solution. 5.43 moles for every liter of NaCl. Notice I've inverted molarity. That tends to be problemsome. 0.0315 liters, or 31.5 mLs of the 5.43 molar sodium chloride. Many problems were assigned here because you just have to encounter a problem and think your way through. So, something else you may be asked is for an ion concentration in terms of molarity. The example, sodium chloride produces 1 mole of sodium cation, but sodium sulfate, it produces 2 moles of sodium cation. So as we show you a practice problem, I've used something where it's a little bit, well, it's not more complicated, it's not a one-to-one. So what if we want to know the molarity of our hydroxide ion given a 0.20 molar barium hydroxide solution? Well, I would say please write the equation, because then on paper you have those 2 hydroxides. So to do this problem, we have 0.20 moles per liter. That's our given molarity. By writing the equation, we see there are 2 moles of hydroxide for every mole of barium hydroxide, and it gives us 0.40 molar hydroxide ion. Again, you may see a problem like this. You'll definitely encounter it in 1220 when you're finding pH and pOH. On the bottom, I put more of an accounting type table. I call it an ICE. I don't know if I should call it equilibrium, but it's another way to solve the exact same problem. So I kind of mentioned a stock solution, and that has to do with a dilution. Often your reagent is more concentrated than you need. And again, we call that a stock solution. And what we do is we dilute that solution by adding water. Now, there's many different ways to solve it. I'm showing two different methods using concentrated sulfuric acid. The sulfuric acid comes to us as an 18 molar. We would call that a stock solution. And we want to make 200 mils of only a 1 molar H2SO4 solution. So again, I put in a lot of the numbers already. Here is what I want. This is what I want. Here is the concentration of my stock solution, and here is the amount of stock solution that I desire. So if I were to do this kind of calculation, I would come up with 11.1 milliliters. You can do it that way. The second way, method 2, you may have seen that before in high school as M1V1 equals M2V2. Fine, as long as there's no stoichiometry involved. So I have my molarity of my concentrated and my volume of concentrated. This is the one that I'm trying to figure out. I don't know what that is, but I do know my molarity of dilute and I do know my volume of dilute. If I were to crunch those numbers, I would once again come up with 11.1 ml. If you use this, make sure your volume units are the same. By that I mean consistent. So this almost wraps up this section, but I wanted to add one more problem that you may encounter. Sometimes it's not going to be really straightforward. Here we want 500 mils of a certain concentration of ammonia. They're not giving us the same inputs we usually get. We're being told that for my ammonia, when it is concentrated, it is 28.0% by mass. Like, what does that mean? And it's also telling us that the density of this ammonia is equal to 0.898 grams per ml. So as we move further into the course, what you often want to do is tabulate your information. Then what you have to do is think, and after that you have to have a plan. So essentially I thought about it and then I said, what am I going to do in order to solve this problem? Well, 500 mLs is 0.500 liters. That's really the one thing that they told us. The other thing they gave us is the molarity that we desire. 0.825 moles of NH3 per liter of solution. So both of these are givens. And now how am I going to rearrange the information I have given? Well, back in the old days, we said 17.03 grams of ammonia. That's our molecular weight. Notice we're able to get rid of our moles of ammonia. So then you kind of scratch your head because you've not really seen problems like this before. But if you have a 28% solution, it is 28 grams of ammonia for every 100 grams of solution. So I would put in 100 grams here, and I put my 28 in before we started. But that's where we're using the mass percent. So we've gotten rid of the grams, and now what we have is grams of solution. Well, when we look at these densities, it really is grams of solution per mLs of solution, and that is the last factor that I used. I used the density factor, 1 mil per gram, 0.898 grams of solution, and as you can see, that gets rid of our third dimension analysis label, and we come up with 27.9 mLs of concentrated NH3. I would say this problem is hard. I would even put the word very in front of it. So again, all you've done is dimension analysis. This is what we did in chapter 1, but it requires a lot of thought. The last piece of this section is mixing solutions. Chances are there'll be one on your midterm. So what we have is a solution of sodium chloride, and we have a solution of sodium sulfate. We talked about these in the beginning part, writing equations, and you notice I wrote one. So there's 3 different sets of ions that you have. You have Na plus inside the beaker. You have some Cl minus inside the beaker, and you have some SO4 2- inside the beaker. We want to know what is the concentration of each of these ions. So here is my sodium calculation, my chloride calculation, my sulfate calculation. Notice what I have is for sodium, I have two different sources. I have some coming from sulfate, I have some coming from sodium chloride, and I'm going to have double the amount from the sodium sulfate. So when I wrote this out, I said moles of Na plus for the new volume. This refers to what I got from NaCl. This refers to what I got from sodium sulfate. And this is my new volume. Lots of numbers, but think about it conceptually. Solution 1, solution 2. I could almost make another Na plus here because one comes from Cl. The other one comes from the sulfate. And when I have the sulfate, I am getting double doses of sodium ion. So those are the numbers as they are crunched, and I come up with 1.666 molar in terms of the sodium cation. The anions are much easier. They only have a single source. Here I have my moles of Cl minus for my new volume. Here is what I'm getting from NaCl, the number of moles new volume. Numerically, it comes up with a 0.333 molar. And for my sulfate, I do the same calculation, and I am again using just the individual sulfate, and I come up with 0.666 molar. Lots of homework problems assigned. I do think you need to sit down and try it on your own. Please ask questions.